Hey everyone! At the end of our last video, we left something unresolved. I dropped a basketball and a tennis ball from the same height and they hit the ground at the same time. We know from Newton's law that Earth pulls harder on the basketball. So why did they fall at the same rate? I'm going to give you the answer today, but first, I need to make sure we agree on something more fundamental. Watch this. At the very top of that throw, the instant the ball was hanging in the air, what was its acceleration? Most people say 0. After all, the ball stopped moving for a moment, right? If it's not going anywhere, how could it be accelerating? That reasoning sounds airtight. It's also completely wrong. And understanding why it's wrong is exactly what we need to answer the falling ball question from last time. Here's the key distinction. Velocity tells us how fast something is moving and in what direction. Acceleration tells us how quickly the velocity is changing, not what it currently is. Watch the ball's velocity throughout its flight. On the way up, it's moving upward, but slowing down. At the top, the velocity is 0. On the way down, it's moving downward and speeding up. The velocity is changing the entire time. It is always changing in the same direction, downward. Gravity doesn't know or care whether the ball is moving upward, downward, or not at all. It just steadily decreases the velocity at the same rate throughout the entire flight, 9.8 meters per second every second. At the top of the throw, the ball's velocity is 0, but it is changing at 9.8 meters per second downward. That is perfectly real acceleration. 0 velocity and 0 acceleration are not the same thing. So what is causing the acceleration? A force. Gravity is pulling the ball downward the whole time, on the way up, at the top, and on the way down. And Newton gave us the exact relationship between force and acceleration. Newton's second law. Force equals mass times acceleration. If you know the force acting on an object and its mass, you know exactly how it will accelerate. This is the bridge between the force of gravity that we derived in the last video and the motion we actually observe. And that bridge is exactly what we need to finally close the question from last time. Last video, we found that Newton's law of universal gravitation gives the gravitational force on a falling object as Earth pulls harder on the basketball than on the tennis ball. A larger M means a larger F. So shouldn't the basketball accelerate faster? Okay, here's where F equals ma comes in. We can set the gravitational force equal to ma and see what happens. The mass of the falling object cancels out completely. The heavier ball experiences a larger gravitational force, yeah. But it also has more mass, which makes it proportionally harder to accelerate. These two effects are not a coincidence. They cancel exactly every time for every object. The result is an acceleration that depends only on Earth's mass and the distance from its center, not on the falling object at all. We call this g. Near Earth's surface, it's about 9.8 meters per second squared, the same constant acceleration we saw acting on the thrown ball throughout the entire flight. It doesn't matter whether you're dropping a basketball, a tennis ball, a feather, or a coin. In principle, g is the same for all of them. In principle, because in everyday life, there's a complication: air resistance. Air pushes back against falling objects, and it pushes harder on objects with a larger surface area relative to their weight. That's why a feather floats down while a coin drops first. It's not gravity, it's air. So let's get rid of the air. This tube contains a feather and a coin. Let's drop them first with air inside. Coin first, feather second, just like everyday intuition says. Now watch what happens when I pump the air out. Exactly what the math predicts. Remove the air, and gravity treats them identically. Let's bring it all back. We started with the question of acceleration at the peak of a throw. The answer is 9.8 meters per second squared downward. Because gravity doesn't respond to how fast something is moving, It just steadily changes the velocity moment by moment. Okay, if you stood on a planet with twice Earth's mass, but the same radius, what would g be there? Twice as large, about 19.6 meters per second squared. Bigger planet mass, stronger pull, and nothing cancels it this time because we changed big M, not the mass of the falling object. Note, g does decrease with altitude. Technically, it varies with r, but for everyday heights, the change is negligible and we treat it constant. Okay, here's what we've established today. Acceleration is not the same as velocity. An object can have zero velocity and a very real acceleration at the same instant, like a ball at the top of his throw. And we can apply that understanding to gravity. Combining Newton's law of universal gravitation with his second law, the falling object's mass cancels out entirely. The result is g, a constant acceleration every object near Earth's surface shares, about 9.8 meters per second squared downward. We've now seen the intricacies of Newton's theory of gravity. As powerful as it is, Newton's equations carry a hidden assumption that turns out to be wrong. In our next video, we'll follow the cracks that led Einstein to completely reimagine what gravity actually is. Thanks for watching, and remember, physics is all around you. You just have to look at it from the right angle.